The de Havilland Comet was the world's first production commercial jetliner produced by de Havilland of Great Britain in 1952. The Comet was a considerable achievement for Britain because it advanced their aviation superiority worldwide. That was until several catastrophic accidents occurred. In January 1954, BOAC Flight 781 experienced explosive decompression over the Mediterranean Sea. Explosive decompression is an unplanned drop in pressure of a sealed system. It is often a result of human error, material fatigue, engineering failure, or impact, which causes the pressure vessel to vent into the lower pressure surroundings. All 35 passengers and crew members were killed during this incident. Initially, it was assumed that an engine turbine explosion was the cause of the explosion. Due to the severity of this accident, all Comet aircraft were grounded right away. Extensive research took place after the first incident, with officials examining the first aircraft. Since it was presumed that turbine issues were the cause of the explosion, modifications were made to turbines in all the Comets, and the planes were then cleared for flight. Just weeks later, South African Airways Flight 201 experienced the same explosive decompression as Flight 781. All 21 passengers and crew members were killed during this accident. This caused investigators to question their original statement of the issue being due to the turbines. A multi-year investigation took place for both flights. It was determined that metal fatigue caused by design defects was the ultimate cause of the explosive decompression in both instances. An important factor in high-altitude flights is that the cabin pressure and temperature are comfortable for the crew members and passengers. The aircraft fuselage needed to withstand high stresses arising from cabin pressurization during high-altitude flights. It turned out that the repeated pressurization and depressurization of the cabin during each flight contributed to the horrific failure of the two Comet flights. There were many contributing factors that led to the failure of these planes. The first is that the squared window design caused extremely high stress concentration at the window's corners. Calculations revealed that up to 70% of the aircraft's ultimate stress under pressure was concentrated on the corners of the windows. A fatigue crack originated in a corner of one of the cabin windows. It advanced until the metal skin was punctured. The second severe issue was that the supports around the windows were riveted instead of glued as originally stated in the design. The rivet holes caused the fatigue cracks to occur because of the repetitive pressurization and depressurization of the cabin during flights.
The sharp right-hand corners of the squared windows caused local areas of high stress concentration that provided optimal conditions for crack initiation and propagation. Peak stress at the edge of the windows was estimated to be 45,700 psi in total, a combination of 43,100 psi due to cabin pressure, 650 psi due to flight loads, and 1,950 psi due to wind gusts. This peak stress was 70% of the ultimate tensile stress of the material. The Royal Aerospace Establishment found fatigue crack growth from a rivet hole at the low-drag fiberglass forward aperture, which had caused the catastrophic breakup of the aircraft at high altitude. The punch rivet construction technique had worsened the Comet's structural fatigue problems. Its aircraft windows had been specifically engineered to be glued and riveted, not with the technique of punch riveting. The imperfect nature of the hole created by punch riveting could cause fatigue cracks to start developing around the rivet, and develop they did. Additionally, circular cylindrical structures such as the fuselage developed internal membrane stresses that were constant throughout their thickness to attempt to resist the internal pressure loads. Due to the curved shape of the fuselage, these forces induced secondary out-of-plane bending moments to straighten out the curvature. In addition, the stress concentration around the escape hatch and window cutouts was exacerbated by countersunk bolt holes, creating a knife edge in both the primary skin and doubler reinforcement. The cracks that grew in a bay from one cutout to the next were not tolerable and resulted in the ultimate failure of the structure. There are several engineering solutions to the problems this aircraft faced that were implemented. Firstly, the square edges of the windows were rounded so as to remove stress concentrators that allowed for the initial fatigue crack propagation conditions. Secondly, the windows would be implemented as originally designed, being installed by gluing and drill riveting so as to not create fatigue cracks that could develop around the rivet. Lastly, crack stoppers could be placed between frame cutouts that could break it into multiple sections. This would help prevent cracks from propagating from one window to the next.